Thank you very much for having me today and having this opportunity to talk about our recent work. So today I'm gonna talk about our recent work on side channel resistant circuit design using high-level synthesis. And before talking about our recent work, let me briefly introduce myself. And I am now an associate professor of Tokyo Institute of Technology, Japan, and I'm working here for since 2014. I got a PhD degree in information science in Nagoya University, which is about 250 kilometers away from Tokyo. And after graduation, I was a visiting scholar at UC Irvine in United States and Karlsruhe Institute of Technology in Germany in 2010 to 2012. And I'm mainly working on system level design, like hardware and software co-design of embedded systems. And so my PhD dissertation was entitled High-Level Synthesis of Array Size from Large Behavior Descriptions. And part of my PhD work was to develop an open source benchmark for high-level synthesis named CHStorm, which is one of the widely used benchmarks in high-level synthesis. Actually, I'm still a very beginner in hardware security, so I may give you very stupid questions. So sorry about that in advance. I currently have some collaboration with professors in the University of Electro Communications, which is which has many good famous professors in hardware security, like Professor Sakiyama, and also advanced cryptography, and like Professor Iwamoto, and so on. So actually we are now trying to make a new project about hardware IP protection using advanced cryptography. So that's why we are working together to figure out what would be the secure and practical solution for that. And this is about our university, Tokyo Institute of Technology, in short, Titech. And this university was founded in 1881, and at the beginning it was started just with the Department of Engineering. And mainly we have the Department of Engineering as well as the Department of Science. And we don't have medicine or pharmaceutical. So actually some political things are happening, and president of our university and also the president of the Tokyo Medical and Dental University decided to merge both universities together from next year. So we don't know what will happen from the next year. But for now, only for the Department of, mainly for the Department of Engineering and Science, we have this much we have this much of students and faculty member. And what is famous for our university is a supercomputer named Tsubame, which was ranked 5th in the world several years back. And our university also have many famous professors, emeritus professors like who have many contributions on conductive polymer and quantum annealing, something like that. And this is the our group. And currently we have one faculty member, that is me, and one postdoc, and 2 PhD students, and one of them is there. So I guess he's going to give a short talk on this coming Friday. And 9 master's students and 3 undergrad students. And as I have mentioned, I have been working on embedded system, how we can design a hardware and software implementation for some applications, embedded system applications. And currently, we are mainly working on machine learning stuff, like neural architecture search, which is to explore the kind of near optimal neural networks structure model using rainforest learning. And federated learning is a neural network on top of distributed computing. And also countermeasures for adversary attacks, which uses fabricated images with the malicious perturbation. And also some security stuff, like hardware security. And one of the topics is that I'm going to talk today. And the microprocessor stuff will be maybe given by my student this Friday. And also network intrusion detection. Actually, this is the combination of security and machine learning. And also, we have just started to work on NTT accelerator for lattice-based cryptography just recently. And we are mainly working on FPGA design, but sometimes we design our chip using ASIC. Actually, this is the work of Jan, my student. Yeah, there. And so my talk today is about one of our recent works to make right-way cipher design resistance against power side-channel attacks, leveraging high-level synthesis technology. We are motivated to figure out to what extent can the designer do for the side-channel resistance circuit design using a security unaware high-level synthesis tool. So in this work, we combine the high-level synthesis optimization and threshold implementation in the behavioral description that is fed into the high-level synthesis tool. And this work was presented at ISFPGA, which is one of the top-tier conferences in FPGA, just a few months back. And the title was Power Side-Channel Countermeasures for ARX ciphers using high-level synthesis. The first author was this girl, Sayar. At the time of presentation, she was still a master's student, but this March she has just graduated, and she's now working for Sony Corporation. And Mingyu, another student who are here today, also has a contribution to this work. And actually this work is also a collaboration with Professor Lee and Sakiyama in the University of Electoral Communications. And before talking about our contribution, let me briefly explain what is high-level synthesis, because not all people would be familiar with high-level synthesis. So high-level synthesis is a hardware design automation technology to translate a behavioral description like C or C++ into the corresponding hardware description written in Verilog or VHDL. So as we can see in the in this figure, in order to get the, for example, for the FPGA design, in order to get the final FPGA bit stream, we need to go through many different steps to lower the abstraction level one by one. place and route is to convert the gate level net list into bit stream, and logic synthesis is to convert RTL description to gate level net list. And on top of that, high-level synthesis is currently getting used in industry as well, because designers can just focus on the behavior or algorithm of the target system. And high-level synthesis takes as input the behavior description and time description, and then high-level synthesis can compensate the missing information, which is very critical for hardware design, like timing and hardware hierarchical structure. So because designers can just focus on the behavior descriptions, so it can greatly improve the design productivity, especially for designing very big and complex embedded systems. So this is very unique in the digital circuit design, unlike logic synthesis and place and route, because the input is the kind of software implementation. So the very important step in high-level synthesis is to decide when to perform what operation, which is called scheduling. And another good benefit of using high-level synthesis is to generate largely different designs from just a single input by applying different combinational optimization. I will explain about this optimization later. So high-level synthesis have been used mainly for data flow-centric applications like DSP applications, and nowadays machine learning applications as well. And often high-level synthesis is used combination with FPGA because they both are good at handling rapid prototyping. And in high-level synthesis, the optimization are roughly two types. The first type is designer-specified programmers, which are mainly used for loops and array optimization. Here's an example of loop optimization. In the loop, we have operation read, compute, and write. So multiple operations are performed inside of the loop. And if the designer specify this kind of programmer directly in the code and where the optimization should be applied, and then the high-level synthesis comprehend this and then try to overlap the consecutive iterations, partially overlapping with each other, so that the total cycle count can be reduced as much as possible. So the first type, this is just an example of loop optimization, and a similar kind of instruction can be applied to arrays as well. The main purpose of this optimization is to extract the parallelism between operations or loops or something like that, while raising the data reuse. And finally, to minimize the total cycle counts. And another type of optimization is two automated optimizations. So unlike the first one, the second type of optimization is not what the designers can directly instruct the tool. And scheduling is a very important optimization step to convert from the untimed to timed descriptions. And mainly it aims to change as many operations in a cycle as possible in order to minimize the total cycle counts, as we can see in the right bottom figure. So this can be applied as long as the clock constraint is not violated. And I will come back to this. Actually, in this work, we focus on the second type of optimization, and I will explain later how we utilize this, focus on this optimization later. And in this work, we focus on ARX-based right-way cipher because their permutations are data-centric. And as I have mentioned in a slide, the previous slide, high-level synthesis is very good at handling the data-centric applications. So if high-level synthesis is used for cipher or IP design, then we may generate different IPs that have different trade-off of circuit area and delay. So this will be very promising. And so, yeah, that's why we focus on ARX and by, focus on ARX when we use high-level synthesis. And in our work, we use these three ciphers, Chasky, Simon, and Speck. And for Simon and Speck, there are some combination of different security parameters. But in our work, we use this setting. And here's then the permutation, data for permutation for these ARX ciphers. And, sorry. So in order to mask the power side channel in those ciphers, ARX cipher, we need to apply masking or threshold implementation. And because we are now using high-level synthesis, it's reasonable to apply threshold implementation in the behavior description of those ARX ciphers. And so in the algorithm of ARX ciphers, addition is usually specified using the plus symbol. But when we use high-level synthesis, high-level synthesis generally translate the symbol, the plus symbol, into ripple carry adder using a carry component of FPGA. We decided to decompose this addition operation into logic operation of Colchester adder because handling both arithmetic burst masking and Boolean masking is very tricky, especially between especially for the conversion between them. So we specify the Colchester adder algorithm in the C code, and then apply threshold implementation. So here's KSA, Colchester adder algorithm. We code it in the C code. Actually, this is not something new because already some software-based threshold implementation work have applied this kind of coding. But what the contribution of this work here is to use such kind of software-based masking approach to their hardware design by using high-level synthesis. Then after applying behavior level threshold implementation, we use 3-share TI here. We now have just rotation, exclusive OR, and operation, and plus exclusive OR operation. And we need to carefully handle nonlinear operation, these two nonlinear operations. Maybe I don't have to explain here that much, but just in case how I briefly explain how we coded these two nonlinear operations. So in our implementation, we define the function, C function, to handle these X, Y, and Z as input to generate the output A. And for the AND operation, we fed the randomness in the 1, 2, 3. So this is how we handle the nonlinear operations in the ARX implementation. Then the code was fed to high-level synthesis too, and the operation when designing ciphers for on FPGA, operations are mapped on logic blocks or lookup tables. And here's a brief overview of FPGA. And in this, here's in case of 4x4 tile FPGA, and each tile is a lookup table. And here is an example of 3-input lookup table. With this lookup table, we can map any logic function with 3 or less input and 1 output. In other words, if we want to map the much more complex, much larger logic functions, we need to use multiple lookup tables, and basically those multiple lookup tables are concatenated. And what is difficult on FPGA design is such concatenated lookup tables are likely to have glitches. And in high-level synthesis, as I have mentioned, it tries to optimize the operation, try to chain or pack as many operations as possible in a single cycle. And that would cause that would generate a complex combinational circuit that is mapped on the concatenated lookup tables. That means by the scheduling optimization, we may have non-negligible propagation glitches between nonlinear operations, which would be a cause of the secret leakage. So we need to handle this high-level synthesis optimization. Recall that our code has now already have a very simple operation, rotation, exclusive OR, AND operation, and plus exclusive OR operation. And because they don't have glitches, they don't have carries, so and they are mainly logic operation. They can be mapped on lookup table with a single depth. We may need to use multiple lookup tables to handle 32-bit, for example, but those lookup tables are not concatenated one after another. So, but as I have mentioned in the previous slide, if the scheduling is try to optimize multiple operation in a single cycle, the generated combinational circuit will be very complex and may cause glitches. So, so in other words, if we can prohibit the high-level synthesis tool to do such optimization, we can handle, or we can mitigate the power side channel. That is counter to the traditional high-level synthesis goal, because it has been trying to make the system as fast as possible. But in terms of security, that would be not good. So in our approach, we try to manipulate the high-level synthesis optimization indirectly using a designer-specified clock constraint. Because designers cannot touch the optimization, scheduling optimization in high-level synthesis 2. So that is the only way, giving the kind of tight constraint to the high-level synthesis is the only way that we can contribute to the scheduling optimization. So I want to say that high-level synthesis constraint is not always the same as the clock frequency that is used for an FPGA board. And that will be fine as long as the timing violation doesn't happen on the actual board. So in other words, we use the high-level synthesis clock constraint just to force the tool to disable the operational chaining. And in our evaluation, we gave a very tight constraint, like 1 nanosecond, which is 1 gigahertz. Actually, this is not practical for most of the FPGA board, which is too much. And so we didn't use this clock frequency for the actual FPGA board. Instead, we use much lower clock frequency of 12 megahertz in the evaluation. So briefly summarizing the contribution of our work, our approach approach combines two things. One is software-based threshold implementation to design digital hardware. And another one is disabling the scheduling optimization that is automatically done in the tool. And in order to evaluate the effect of our approach, we implemented 4 methods with and without these 2 approaches. The first one is the default setting, in that we don't apply threshold TI, or we keep the chaining, operational chaining. The second one is the second method is not to use TI, but disable the operational chaining. The third one is to use TI, but the operation is still chained. And the fourth one is our approach, in that we use TI and disabled chain optimization. The evaluation was done for the 3 ARX ciphers that I mentioned previously. We used a SAKURA-X board, and the evaluation was done for the clock frequency of 12 megahertz. We evaluated the potential leakage by t-test for the 1 million power traces. We thought that it would be better to actually attack the ciphers, but we are not very professional about hardware security yet. So for this work, we just evaluated the potential leakage. And also, we evaluated the overhead that was caused by the TI application, and also disabled the chaining. And here's the security evaluation result on Chasqui. The A is the default setting, so we didn't apply TI, and still we still used operational chaining, and only for Chasqui, only our method could mitigate the leakage successfully. And what is important here is just applying in TI couldn't prevent from leakage. So here what I mean is C, the left bottom result. The similar results were observed for Simon as well. And here the method C looked that it doesn't have the leakage, but actually it had some points that exceeded a threshold of 4.5. And finally, for spec, interestingly, not only our method, but also the method C that applied the threshold implementation, but still keep the operational chaining, also mitigated the leakage successfully. And here's a brief summary of the security evaluation. Because these four methods resulted in different ratings, total latency for the per permutation. So here we compared the ratio of sampling point that exceeded the threshold of 4.5. And only our method could mitigate the leakage for all ciphers. But as I have mentioned in the previous slide, for spec, C also worked well. So it is quite difficult to understand what was happening in high-level synthesis too, because there are many complex optimizations have been applied, not only about scheduling optimization. So for now, what we can say about this result is that the number of operations per permutation have a very strong correlation with the potential leakage. Because it's most likely because high-level synthesis too should have much more opportunities to optimize the multiple operation altogether. So in that sense, spec has the least operations per permutation, and that's why even without disabling the operational chaining, it could luckily mitigate the leakage. But that happened only for spec, and we think that we should evaluate more different kinds of ARX ciphers to confirm our finding would be reasonable or not. And finally, here's an overhead that was caused by these four methods. And as expected, our method has a very large overhead in both on the area and delay. And it is natural to have the overhead against the default setting, which doesn't have the masking or chaining disabled. But because we have already triplicated the number of operations. But it is kind of critical to have this much of overhead against the TI applied but operational chained version. So after this evaluation, we try to reduce the overhead with combination of designer-specified programmers as much as possible. But unluckily, we fail to reduce the overhead so far. So we need to examine what happened particularly for spec, even when we still keep the operational chaining optimization. So here's the conclusion of this work. In this work, we explored the cipher design method using the current security unaware high-level synthesis technology. And we found that even the lazy high-level synthesis designer can handle the leakage-free cipher designs. But that works only if the overheads are acceptable. But that overhead is really large. So we need to carefully study security-aware optimization so that high-level synthesis can contribute to design different versions of IPs with different trade-off of area and delay. And so far we have, through this evaluation, we've seen that chaining in high-level synthesis should be a key to secure or unsecure the high-level synthesis generated circuit. But we also need to carefully see what happened after high-level synthesis. Because after high-level synthesis, we still need to do many different optimization, like in logic synthesis and place and route, and those optimizations should also contribute to security as well. But for now, we've seen that, of course, we need to think about those optimization, but we've seen high-level synthesis should have non-trivial contributions to secure hardware design. Yeah, that's it.